And so that's a pretty substantial effect. Now, the difference goes even one step further, that not only do the brown adipocytes have a much higher metabolic rate, but then the question is, what for? And that might sound a little academic of a question. What for? What is the metabolic rate for? By that, I simply mean, what is the cell burning that energy for? Because a cell will normally burn energy based on what the cell needs. And for example, muscle and even fat tissue, basically the muscle or the fat cell will say to the mitochondria, hey, mitochondria, the cell, all of the cell, we need this much energy to do our job. So give us this much energy. And that process is very coupled. That's what we call it. It's a very tightly coupled process. An analogy for this would be like someone who's driving a stick shift car and they're revving the gas and they see the RPMs driving up, really revving up, but they're keeping their other foot on the clutch, or the car isn't in gear. And so the speedometer, the actual amount of movement in the car, is nothing. It's not matched. So the RPMs are revving, but the speed isn't moving at all. That's uncoupled. That's when we've teased the two processes apart. So the instance I was just talking about, we're revving the gas and we're moving at the same time. The car is in gear and it's going down the road. Now, as I mentioned, in the uncoupled state, which is what we have with the mitochondria in the brown tissue, that's basically when the cell isn't demanding work from the mitochondria. The mitochondria just keep burning energy. So we're revving the engine, but not because the cell needs any work done. It does, but its needs are adequately met. In this case, the mitochondria in the brown fat cells are uncoupled, as we say. And in this case, they are just burning nutrients. They're burning fat. They're burning glucose for no cellular work that the cell needs done. It's just to create heat. And heat is a chemical like waste. A biochemical waste. It is sort of the sign of a wasting of energy, back into the universe, if you will, or into the atmosphere. But in the human body, that does serve a purpose, particularly when we're babies. A newborn baby has a relatively high amount of brown fat. So amidst all the chub on the baby is a relatively high amount of brown fat. And this is good because the newborn baby doesn't have enough muscle to shiver very well. And so it stays warm. If you lift your adorable little baby out of the bathtub, and he or she is going to stay warm, not by shivering, but by having all of this brown fat that suddenly turns on and starts chewing through nutrients just to create heat. Now, as we grow and our muscles grow and our body changes substantially, the relative amount of brown fat we have drops precipitously. And then much of the fat we continue to gain throughout our life is white fat. And that's okay. It works because if we're cold, we can shiver. However, we know that adult humans who have more brown fat or whose brown fat is more active, and we can talk about that, they are much more resistant to diet-induced weight gain and diabetes and other cardiometabolic complications. Now, on the human body, the white fat is basically the fat that you can pinch and jiggle. That's all of our subcutaneous fat and a little bit of fat within the abdominal space called visceral fat. And then humans have designed little pockets of brown fat kind of sprinkled throughout the thoracic cavity and up into the neck. Now that's not a lot, but my lab has found that when the white fat cells start consuming ketones as an energy source, they will actually enhance their mitochondria number, and the mitochondria will be more uncoupled. So we found in humans that when humans were in ketosis, their fat cell metabolic rate went up by 3 times. Now, that didn't get up to the 10 times higher that you see with brown fat, but still a tripling of the metabolic rate of fat cells is nothing to sneeze at.